Hello. We are Team R44. We are Pratik, Yorgos, Alexandra, and me, Eva. We are from Sajay Bhushan Studio. Our project is called Wired, and our research is about the generation of active bending structures through the use of industrial robotic arms in a larger architectural scale. Well, investigations into material and robotics in the field of architecture have begun to challenge the architectural discourse by proposing alternatives to conventional modes of practice through the adoption of new fabrication technologies. The aim of our research is to create a process that ensures continuity between the stage of design and the materialization of the final outcome through the customization of industrial robotic arm technology. Taking for granted that the introduction of new tools in architecture alters the way we perceive and drive manufacturing, our research aims to formulate a new fabrication method that generates and addresses new formal and tectonic challenges. We contribute to the wider architectural discourse a way to develop the initial stages of active bending formations in architecture. Through integrating robotic arm technology in the construction process, we envision their potential application to larger architectural scales. From a wider perspective, what we want through our research is to introduce a new tool in architecture, industrial robotic arms, and to create a new material to build with. So what we need is a new design process in order to combine the two and make architectural space. Through our research, we have investigated several case studies concerning material, robotics, and active bending structures. Materially, we have seen case studies like the textile hybrid or bamboo structures that have very similar structural behavior and material behavior as the material that we are creating. Concerning robotics, we have seen several case studies that inspired us, which create customized processes through the customization of the tool with customized end effectors. And in this way, they don't just simulate already existing fabrication processes, but they try to reimagine the design as a whole. And we have also investigated case studies that are active bending structures in order to understand the structural behavior and get inspired and create our own material system. So in an overview, the material we're going to talk about and that we have generated is consisted of fiberglass rods, spring steel, and nylon coating. And our aim was to create a composite material which has phase-changing behavior. So by being a composite, it could be scaled, and we could create a continuity of structure. Moving on, an overview on the industrial robotic arm use. Concerning the issue of zero tolerance, that there is a discourse why robotic arms are used in architecture and how precise they can be. We want to achieve implicit control, which means that we want to give part of the control of the tool, we want to give part of the precision in order to allow the material intelligence to show us new architectural forms. And concerning active bending structures, through our research, we found out that they are non-linear and unpredictable. So this means that we need to create a new form-finding process customized to our own concept and generally redesign the design system at an early stage.
So in terms of programmable material, we are using a composite material, which, as Eva said, combines the high tensile strength of the piano wires and the fiberglass, and the low tensile strength but the compressing strength of the plastic. And in this specific situation, we are using nylon. So we are creating those flips in setup that you can see in the right hand, and we are freezing into position so as to get the deformation, the elastic deformation of the wires through a thermoforming process. Initially, we are trying to calibrate our material behavior by loading single spring steels and changing the scale and the thickness of those. And we see that the thing that we are really interested in is this elastic deformation. We are also doing material experiments in terms of nylon. We are thermoforming the nylon, and we are calculating the times that is taken for individual nylon tubes with different thicknesses to melt. And then we are combining those two materials and in low resolution studies, and we are moving the anchor points so as to see the deformation and the lattice formations that we produce. In higher resolution studies, we are creating the same setup of material, but we are moving the anchor points of those material experiments in the XY plane so as to investigate the formation, and we have branching results, as you can see. We continue moving in translation in the Z-axis and rotation as well, and we have these results. And those are studies of global deformation. Elastic bending structure is the global deformation, the thing that is given to us. And we are continuing having the same material experiment, the same transformation, but in different sequences. And we are investigating again the results that we have. And here we are investigating the local deformation of our material experiments. So we are changing the heating time. We have the same material experiment, the same setup. And the interesting part of this process is like the global deformation is also influencing, as you can see in the last picture. So in the last part of the material experimentation, we are comparing a manual process versus a robotic process. We have the same material setup, and we are trying to apply the same forces, one manually and one robotically. And the interesting part is that, as you can see, the result is totally different. The distribution of forces in the material experiments we produce through robotics is it's equal, it's much more equal, and the result is more harmonic. The same with the three-branch experiment. And the same observation, the elastic deformation that the robotic arms are giving to us, it's much more interesting.
So now we move towards robotic fabrication.
We saw that the introduction of new tools profoundly changes the way we understand and perform manufacturing. So in order to do this, we need to thoroughly explore the tool's possibilities in order to use it creatively. In our robotic research, we started by investigating robotic arms' limitations and potential in a smaller scale first, using a Lynx motion robotic arm. And we achieved to control its movement to a satisfactory level, and we also connected it to an Arduino board, and through sensors we achieved its real-time interaction with the environment. And finally, we tested different scenarios of small robotic arms, choreography and coordination. And moving on, we extended our robotic experiments to a larger scale using industrial robotic arms. And we intended to capture the movement of the robots physically through long exposure photography and digitally, visualizing the robotic path, so as to understand better its space of occupation. So having in mind that the final goal was to actuate and deform a structure through a pop-up process, we speculated on the actuation of the robotic arms. We need movement in all 6 axes, something that can be performed only by a 6-axis robotic arm. So it's the only tool we can customize in order to construct our architecture. So moving on, one step forward, we created a 3-dimensional grid of points, which these points are differentiated because the limitations of the tool showed us that the robotic arm cannot reach all of them. So eventually, we can find out the map of reach of the robot in all axes. Why this is important in our research? Because using the robotic arm to actuate structures doesn't mean that we can design everything. So we have to use the limitations of the tool in order to alter our design and have feedback from both sides. And in this case, we also investigated by moving the robot which movement is more effective according to how many axes are actuated and how big the angles of movement are. So we can create differentiated zones of actuation.
All right. Our robotic experiments focused on bringing together the material knowledge and the robotic coordination. In 3 diverse trials, we tested aspects of our hypotheses and their actual applicability. Keeping under control the base aspects of each experiment, we understood that the first one, the 1 meter approximate column and the 4 split strand, failed in certain aspects because of its material integrity. We tested principally spring steel, and due to its weight and inability to overcome gravity, it failed. And we were forced to take into account that perhaps it would be best to incorporate another material, something that could withstand both the movement of the robot and could stand and apply the adequate force to the system. In this particular case, we used fiberglass rods. We used 2 types of configurations for the last 2 tests. The first one has on the right has the core of fiberglass within it, and the other one in its exterior. Under these conditions, we understood that the material was reinforced and thus tested it by adding the fiberglass. And in this particular point, we also, in conjunction, tested the robotic movement to understand both anchor points and control points and what they would do to material deformation. In the last experiment with the fiberglass core, the active bending actually was incorporated into both material behavior. So we achieved both what we needed in terms of what the system required and what we expected our architecture to be able to accomplish.
So observing these 2 strand experiments, we formed the last big experiment, like testing different connection networks through the strands and trying to find one that creates more 3-dimensional space as we wanted, and that the constraints don't stop the structure from bending. So we chose one configuration that would create a connected network that, when actuated by the robot, would give us a result of quality that we needed. And these are the photos of the biggest material experiment we created with the robots.
Thus, bringing together every aspect of the robotics, we understood that in order to customize our system, we had to to actually actuate 3 parts: the generation of the material, the transformation of the material, and the setting of the material. And in that sense, we came up with our own end effectors, one for weaving, one for gripping, and one for heating, which are the ones you see up at the front as well.
So in terms of weaving end effector, we are focusing on the operation of looms. The interesting part of the loom is how they weave the material and which parts are moving and which parts remain stable, so as to produce this result. And we want to attach this logic to the robotic arm, as you can see in this experiment. And yes, we found this image like 2 months before. This is a project from NASA that they use carbon fiber, and they are weaving carbon fiber so as to produce this kind of strands. And here we are. This is the first version of our end effector. The weaving end effector is a low resolution end effector that is using another material, threads in this specific situation. And we are focusing on the use of the planetary gears, which allows with one single input to have multiple outputs. So we go a step further. From 3 outputs, we went to the 32 outputs, as you can see in this end effector. But again, the thing that we want to do here is like to automate it and to create a continuous material so as to feed the end effector with material from the back and to produce a weave strand on the front that we can use in the skeletal structures that we produce. And yes, here's a first try of the end effector, and here is attached to the robotic arm. As you can see, the most interesting part in this experiment is the sliding of material that we achieve through this configuration. Here's an exploded version that describes how a wiper motor is giving the automation. And the interesting part in this end effector is that we can program it by changing the rotation speed of the wiper motor or changing different other variables as the feeding points and the relation between rotation and the movement in the z-axis. And how we use this? We structurally evaluate our results, our geometries, so as to see where it's needed more material. So that means that it needs more rotation. And in this simple diagram, you can understand that in the places that we have more material, we have more biggest rotation speed.
In order to control the second aspect of the robotics, which is the gripping, the control points, and the anchor points, we designed also another gripper, versions that we tested in both the actual experiments and the ones that we come up with for the actuated system. In these particular cases, these are all mechanical end effectors, which we operated by hand in order to both attach the strands and to actually mount onto the robotic arm. In the actuated case, the gripper is controlled by a microcontroller and in essence attempts to kind of bring together the concept of actuation and allowing the system to almost be able to kind of sense itself and sense where all of these kind of mechanical points then get applied. And this is a test in the robotics as well. All of these aspects were then pushed forward to the last part, or the last end effector.
Coming to the heating aspect of the project, we tested 5 different methods of heating. Firstly, the heat gun, which worked well for us, but the material takes a longer time to heat. And then we took on to boiling water, which unfortunately doesn't melt the material, but instead strengthens it because nylon has a tendency to absorb moisture. And thirdly, we tried passing electricity through spring steel, but the spring when you pass electricity through spring steel, it decarbonizes it and reduces its structural capacity. Going to the next method, we tried induction coils and we hacked the halogen room heater. The induction coil works well, but develops high heat energy, which needs to be dissipated into a certain medium. So the halogen heater worked the best for us, and it heats nylon of different thicknesses within a span of 120 seconds. So it works well for us. And this is the video of where we attached the halogen and the heating end effector to the robot and deform the material. And then here we have the thermal camera captures of the big model. As the model was being heated, we took thermal. We noted the temperature of the model at certain specific points over a period of time. And this is an axonometric view of the exploration view of the heating end effector.
Ultimately, all of these components come together to form what we call the robotic cell. We know that, for example, each of these components needed to both use some pre-existing conditions. They needed to exist within a factory, and because of the range and reach of the robot, specifically ours, which is an IRB 6640, which can carry about 235 kilograms per payload, has a weight of approximately 1,300 kilograms, and has a rotation of a primary axis of 170 degrees to an axis turn of 360 at its wrist. But however, the reach was a constraint, which is about of 3.2 meters in forward and 3.6 in height at its max. Due to this, we thought, or we came up with the concept of creating a cell which had an extension on rail and had the ability to move towards all of the specific reach map points that we plan out for each of these structures, and be able, especially to reach it with a heat sensor. The maximum length right now at the moment of our structure is about between 12 and 15 meters in length, and then in width it's about 8 to 10 meters. In specific, this is just a component of the robotic cell, the initial setup, which is 2 robots. It has the ability to, or the flexibility to carry 2 to 6 robot arms on it, depending on what was necessary, and thus all of the pretty much the cell which is needed in order to actually actuate and operate a robot for safety reasons. In this particular slide, we walk through the 3 phases of the robotic cell. The first, which is the weaving, the second, which is the transformation, and the third, which is the heating. And eventually to come up with our own robotic coordination, which, there we go, which kind of explains what the process would actually look like, more or less, if this were to actually take place. In this particular case, you see the weaving. 2 robots are laying out the material strands. The only part that doesn't get actually actuated are the control points that we incorporated into the formation to create constraints. All of these are used in order to allow for the pushing force to lift and actuate the material itself. This is the gripping phase. The actual pop-up concept, the architectural component that we are testing and hypothesizing on. And finally, we arrive at the heating phase, which takes place to set the structure in place once the anchor points are set up. And finally.
So, observing the material behavior of our system, we made a research on active bending structures, which have the same formation process and structural behavior. Bending active structures are structural systems that include curved beam or shell elements, which base their geometry on the elastic deformation from an initially straight or planar configuration. In these structures, the generation of form is directly influenced by the characteristics of the material, and what matters more is the formation process, not just the structural behavior or geometrical definition alone. For this reason, we are creating a new design process, customized to our material and to the concept of using a robotic arm for the final fabrication. In order to do that, we approached the early design stages from 3 different points of view. The first one was the empiric, by making physical models and try to understand the material formation. The second phase, the second approach was the numerical, where through digital simulations using a physics engine, we tried to see how we could generate intricate formations by giving inputs such as the network formation, the constraints, and the movement of the anchor points. And lastly, our final approach was a geometrical, where using all the experience and the observation we gained from the previous 2, we tried to create a form-finding process and to define our geometrical architectural elements through creating digitally and testing physically several formations. So concerning the empirical approach, we started by very simple experiments, try to understand how the weaving processes work and what this means in a material system. And then we tried to constrain strands of metal wire and transform them, deform them in space through rotation and pushing to understand what popping up means. Furthermore, we started creating scaled physical models in order to understand how we can control the placement of these constraints, of these connections and anchor points, the nature of those, and how to start programming the construction, the creation of architecture. Because as we said, these systems are non-linear and unpredictable. We started to try to understand what putting flat strands on the floor means and how we could actuate it in order to pop up a structure. And then, furthermore, we tried to see how same configurations of wires and anchor points, but different topological connections can create different kinds of spaces. And in these three cases, by moving only the mid-anchor points, we can create either separated spaces or one bigger one in the middle or linear ones interconnected. So in the numerical approach, we tried to simulate the behavior of the wire and the fiberglass, trying to put all the connections and all the inputs we would put in reality, and try to figure out what this would give us as a result. So this is the pop-up structure we would get through this process. And these are several examples that we investigated, different points of anchoring and different planes of reference and different constraints. So overall, what we observed from all those studies is that the generation of the initial setup and the deformation process is what matters more. In the initial setup, tangential connections join the strands and create stronger structural networks, while cross connections differentiate the space that is created. Similarly, tangential anchor points create transitions from top to ground, and vertical create arches. These actually are the main design tools or the rules that our system provides, and with those we can program the design and the creation of space. So in our final stage of the geometrical approach, at the beginning, in a very low resolution, we define the basic volume of occupation and the space separation. And then we generate a low resolution control polygon, which we manipulate in order to extract later the main curves of the structure, as you can see with the blue color. Of course, these curves are an approximation, but this approximation is based on a physical and numerical simulation, and it gives feedback to the design system. And then we generate the primary structure, the secondary one, and the surface using different rules. The primary structure is consisted of strands, as we saw the material that we create. The secondary is tensioned wires, and the surface is a thermoformed plastic following the same logic that we have throughout the whole process, that we deform and then we set through a thermoforming technique. So these are several iterations and an exploring process using those low resolution control polygons in order to generate different formations. And we investigated using one plane of reference, two planes of reference, where the second one is a more structural core and the first one creates space around it. And in the third case, we tried to figure out whether our system can create vertical elements.
Coming to, once you get these low resolution polygons, we array them in a linear and circular fashion, and then subject these linear and circular arrays to two deformations. Firstly, one where we merge the vertices of the polygons to create primary structural lines, and then we bridge the second condition being where we bridge the edges to generate surfaces. So depending on the spatial requirements, the polygons can be deformed to acquire the primary curves and the surfaces, as can be seen here. These are the circular arrays, where the top row shows the first condition where the vertices are merged, and the second row shows where the surfaces where we bridge the edges to generate surfaces. And here are the curves, the primary skeletal curves, which get extruded from the polygons. Which brings us next to the secondary skeleton and the surfacing. The secondary skeleton is then is then reinforced into the primary structure depending on the structural necessities and the spatial requirements of the shell, and then eventually surfaced using the shrink wrap material, which gets tension between the primary curves and then relaxed using the thermoformed process. And these are the few iterations of the secondary skeleton, depending on the logic of intersection, density, and perforation and the spatial requirements.
So overall, we want to speculate on the spatial qualities of the structures that we create. And we want to create an ambient atmosphere where the lightweight structures that we are creating, although made fast by robotic arms, they can provide a high level of complexity concerning forms in all scales. In a small scale, the melting of the nylon can create intricate formations, but also in a larger scale, the combination of those structures, as Pratik said, can generate complex spaces. So we envision the creation of spaces where light comes in and reflects on the material, showing its texture, and we envision the creation of high-quality architectural space where, while the fabrication process of each part remains the same, the forms that are created are unique and can be used in different urban conditions. And we have to show you one video of the fabrication process of our big model to understand the overall process of the generation of form. Music?
Sorry for this. Sorry for this.
We lost the music.
Yes, but where's the...
Well, you can see the fabrication of the material and the strands. In this case, we weaved them manually, whereas in our system, we say that the robots will do this job. You can see the core fiberglass and the plastic weaved around it. We control the robots through and then we plug the structure on the robotic arms because it needs too much force for the deformation. And we deform it, popping it up, bending it. So as to form the structures that we want. And we observe that even if we program very precisely the whole process, it is very interesting that the material intelligence will give us one new piece of information every time we make a new experiment. And here you can see the heating process, melting and connecting, joining all the nylon tubes together to set the deformation. When it cools down the material, it becomes really solid and stiff in comparison to the flimsy initial setup.
Though this heating process is a lengthy one in this particular case, all of the entire system is meant to actually take all of these components, all of these parts to generate the model and to automate them. and finally, hopefully, to end up on something moderately looking as what we have when we produce them manually and robotically in sync. And thank you.
Here is our initial studies in terms of design, and this is the experiment that we did in RoboFall in small-scale models, and the connections that we test. Here is the experiments that they test. They observe like the differentiation between the manual and the robotic process. The initial studies of planetary gears, our end effectors, the weaving one, the gripping one, and the control points one, our 3D printed models, the design ones. Yes, and at the end is the big structure that we produce in RoboFall. Thank you.
I mean, it's interesting to reflect back on how long the gestation of some of these concepts and ideas are. Looking at John Fraser's lecture and saying that exactly 20 years ago he created that kind of actuated material spline machine. Obviously there are certain intricacies in your model which go far beyond that, and I think it's worthwhile to point out that this popping up, which I really love as an idea, the laying out of a topology and then popping up, but it's more than just the popping up, which through lateral translation, or like Fraser yesterday, simple up and down, that you need all the degrees of freedom or axes of the robot, because you generate in a moment connection. You're gripping that, each of these wires, and you're gripping it from two ends, each of them then having a differential coordinated bending input, potentially torsional input, as if you would take a wire into your two hands, and now the space of variation you can explore, which we do intuitively, how much is actually involved computationally to do that becomes revealed in your project. So it seems very simple. In fact, this is a feast of technological exploration, where you had to go through a number of problem-solving exercises, but also you rely on the robotic intelligence and how we can digitally control them and so on. And so this is for me very interesting. All of the things we take for granted when we work with our hand, and I think it's one of the themes of Shajai's work, the embodied intelligence in craft is so complex and tacit and unexplicit, and we only start to appreciate that now as through the attempt to mechanize and make these explicit processes and knowledges. And I think strikes me in this project. And I think there is this kind of really an elegance in the end of that popping up moment, and the way you said that even with the nearly hidden parameter of the kind of torque input at these points create that space of possibilities. I think to emphasize that and its distinctiveness is very important, I think, in the presentation and in the final depiction.
I like what I see very much. I have only a minor objection to something you said. When you say that what you do is non-linear, hence indeterminate, which is probably true, but there is one philosophical risk inherent in this statement. When we say that we do stuff which is non-linear, hence indeterminate, there is the possibility or the risk to start thinking that philosophically speaking, we create an object which is almost endowed with free will, with a capacity of volition, which is what is inherent in our notion of embedded intelligence in the materials, etc., etc. This is, in philosophical terms, a very risky statement, because if we admit one thing is to say that object is indeterminate, it probably just means that it is too complex for the means of calculation at our disposal. If you posit that it is philosophically indeterminate, you confer to that object a degree of volition, and you make it equivalent, philosophically speaking, to my cat, right? Now, if that were a cat, at some point it would jump out of the table and go and look for a dish of milk. Your object is not going to do that. So we should keep in mind that when you say that it is indeterminate, we are probably speaking a little bit metaphorically and not philosophically. It means that it is too complex for the means of calculation at our disposal. And then you have to proceed by physical form finding, which is exactly what you did, which is a traditional attitude of the craftsman. You make it and you break it. And if it breaks, it's not good. You make it again and you break it, and if it breaks it again, it's again not good. And you keep making it until it doesn't break, and when it doesn't break, it's good. Physical form finding. It is, as you may have noticed, a very laborious and time-consuming process. So my guess is that the way to go at some point will be not through physical form finding, but through computational simulation. Meaning you make it and break it, not in a mock-up, but on the screen. It is much cheaper and faster. But here I stop.
Just to continue what Patrick was saying, I think, like, firstly, I have to commend you for, like, the various strands that you have investigated of various steps of what we took for granted of using our hands, and then being so specific about developing technology and studies simultaneously for each individual step. The other contribution, I think, which is also somewhat hidden, is that most of the electronics that you have developed is significantly cheaper than anything that is available in the market, or something comparable. For example, that NASA winding machine with a robot costs like 1.7 million, and yours doesn't cost anything near that. And that is something, again, another hidden contribution. I think, for your book and things, you should emphasize the technical but also the discursive potential of something that is so easy to make now that you have invested all of the research and the iterations to do that. So I think the value of your contributions is not only in the overall coming together of the various steps, but individual steps themselves have so much hidden value, and as Patrick said, I think you should bring it out even more, in the way you position the project.
In the end, it's an absolutely stunning body of work. Is this on? Hello. Stunning body of work, and then in the end, we're again at the far right, this rendering of the space that it kind of produces, and I guess I'm so intrigued up until a point, and then the design process seems to be sort of almost expected. It's not surpassing, say, my expectation of this kind of structure, and I don't really know what that is, but it doesn't seem to be yet offering up a kind of a new kind of spatial condition, a new kind of material condition, just by the way you're sort of presenting it. But I do see, I'm sitting in front of these models, and I'm seeing some things that are, for me, incredibly novel, right? The kind of emerging of those two strands, I think, is absolutely gorgeous. The way that they begin to kind of cross-knit, and you kind of really sense that kind of elasticity, and so there is some incredible moments kind of beginning to happen there, and so I'm actually super intrigued with what the potential of this is, and it's such a strong, these machines, these weaving machines, I think are so incredible, and I would love to just know more about what they could kind of begin to produce. And maybe it's just in the tweaking of those things, maybe they're kinetic, and then some of them are producing highly kind of porous, very, very, very stiff columns, and others are very dense. But just knowing more materially about what this is going to produce, because you're doing so much, this thing is doing so much work, and it's so manual on a certain level that you really want it to be producing kind of extraordinary kind of spatial conditions.
I want to pick up on where you left off, Mario. I think you're absolutely right that the way to approach these things is by pre-computing and simulating. But I think this project is one of many which shows actually the shift which is happening. So, of course, we've had a reignited interest in bending active structures because we've got much better at computing them. So Jan Knippers and Achim Mengers, etc., is this exactly this, that we can pre-compute well enough now that we're comfortable to do it. But this project speaks to another thing which robotics is opening up, which is that even when we can't quite pre-compute, then we can, if we can pre-compute close enough, then we can go in to a system which is inherently more volatile than we would like. But because the robot can have a force torque sensitive end effector or joints, and because it can scan its products and change them as we go, that the complete pre-computation of the form is not necessary anymore. And that we can go in and produce things, embracing and dealing with that volatility, which is a dramatic shift away from our building industry, which of course has dedicated the last 100 years to ironing out all of the material variation from timber. The whole entire engineered timber industry is exactly denying the timberness of timber. And I think it's very exciting that these kinds of like your own created material, but that even though you can't completely understand it ahead of time, that you can still actually deploy it in an active way, in a useful way, because of the shifts to modifying our instruction set as we produce, rather than having to know everything ahead of time.
Yeah, I just want to kind of pick up on Mario's point, following your lead of the cat. When John Conway was asked about where complexity resides, he said, mathematics is easy, my cat is complex. And the reason for that, I think, is part of the undertaking here is also to understand that we don't need to make a virtual model, a simulation, to sort of act in the world. And I think one of the fundamental attributes, or at least the things that I try to appreciate quite a lot in what Sajay's world is at the moment, is the fact that we should look at these prototypes as actually self-calculating, forecasting simulations, but not virtual, where the behavioral aspect is part of the fundamental kind of mode of inquiry. Because I agree with Jason that there is a kind of difficulty in seeing the simplicity of some of these forms, but they're not because of the elegance or the simplicity. It's because when you see the prototypes, the redundancy, the complex knotting, this idea of how long the length could be. If this is an extrusion process, we could continuously feed the machine, and even the idea of actually fixing it into the ground or coiling it or creating kind of other categories are kind of left to the relationship between the material, the processes, and really about kind of the discovery that's going to happen. And I think part of the challenge that we have is to recognize that there are some leaps that we make that really kind of undo some of the things that we've actually found and discovered. And one of the reasons why sometimes this looks linear in the evolution is because they're happening in parallel. And I think part of the objective that the students have to also try to get their head around, and we do as faculty and teachers, is to understand that these kind of things at some moments, like we never really get a single strand. In those models, we always have 3 strands coming together. So the idea of the notion of how the line in space is interacting with other lines has just generally been touched here. And I think that that's where you can also start to find potentials of moving this forward. The big prototype for me is fantastic. The individual line is also quite beautiful. The notion of space making, I think, should be understood almost like Konrad Waxman was talking about, where he thought that he really wanted to be in the topology of the rope. He wanted to be inside that space And he saw that as something of great value, and he actually tried to reconsider this whole notion of a space frame based on that. Continuous, weaved actually through spaces. There is something about the strategy of the approach of what's at hand at the moment that kind of lends itself to that. And there is this conversation that's happening here about the orthodoxy of symmetries. It would be impossible in your world to create symmetry. But to be honest with you, it's part of the unsaid kind of interest, obviously, that you had from the beginning to actually work with things that actually exhibit behaviors and resistances that become much more dynamic in the ways that you kind of operate with them. These short ones are quite domesticated by the robot. These longer, 3-segment longer kind of elements now start to exhibit a way of working that necessitates almost like a martial arts effect of how you actually respond and react. So I just think that there should be a kind of openness of interpretation and the next step of discussion, because I think it actually does become, similarly to what John was talking about, if it was a spline generator and you could actually design your structure as a single continuous line, what would that world be different than this one, which is actually very much more about tangential convergence and fixed point interfacing with the ground, and it just kind of opens up a different realm of discovery. And I think you owe it to yourselves, I think, to open up that conversation a bit, because that's obviously not where you've really focused much of the attention. It's been on the process of the materialization aspect, right?
I'm sorry.
So,
Please go ahead.
so from my perspective, so my background is more engineering, so robotics. So I'm really intrigued by the design on one side, so it's really amazing, the design that you can create with this process. But I'm also very much intrigued by the richness of the process, having a structural component using strings, so fibers, and a sort of matrix, which can change its viscosity, its softness, its rigidity. So I think this is a really powerful way how to modulate structures from an engineering perspective. Now, you use this to have a form-finding process to come up with a structure that is then rigid, that it found its structure, so it found the final form. Now, did you think of how you could use this to have a living structure that wouldn't find it, but would be alive and have an embedded intelligence, going back to the intelligence question from before, of what is intelligence? Now, for me, in robotics, intelligence is more something that happens when we have a living system, something that changes, that moves, which is embodied. And how can you use this process to benefit from this living aspect of it? How can you change it so to get new perspectives in design and architecture? So I don't know if you can expand on that, or just open discussion.
I just want to pick up the strand from over there where, about the requirement of simulation, but at the same time having only a loose fit or approximated form of simulation. We need to narrow a space, but then we become tolerant of willfulness, which is indeterminacy in the sense of not being able to calculate. And although there's a dream of the total calculability, but that of course is a whole different ethos. As you said, in the construction industry, it's all about precision and constraining tolerance. And here we need to have much more loose fit acceptance of tolerances, because we have contingency absorptions on the next subsystem. Right, that's why is the concrete has to be brought into a certain, up to a certain 30 millimeter, because there is another subsystem coming in, the facade, which needs to come in, which itself, in terms of aluminum profiles, is only 10 millimeter tolerance, etc. That's why I think it's important to bring that force here when you do have a second subsystem, and only then it really becomes an issue, that this is able to pick up and adapt and be malleable to that extent, even if the ranges are a meter and more. But what I'm starting to think of more and more, that the final subsystems, all of this resolves, and I'm starting to think of how to bring it into the model. It's a life process which has to tolerate that. in precision and evolution, where we're not obsessed with measured modularity and fixed conditions. Where we like transitions, we like indeterminacy also on the level of the social and the social process. I think it's very important to say that because we need to bring also all these explorations into the heart of the discipline's core competency and societal responsibility, and look how it plays into our categories. And I think I want to remark that this changes the values, performance values, and our aesthetic sensibility. The kinds of things you find beautiful and adjacent, and the same spirit is coming from Theo. About what we find beautiful is precisely that degree of indeterminacy, that looseness, because that's what we also want for us and for institutions. And I think, which leads me to the reflection about teasing out, and that's why I defend these kind of renderings, by the way, always how this all feeds into our particular core competency, which is orchestrating aesthetic nuances and sensibilities, performance aspects, not necessarily technical performance, but social and societal performance of these structures, how interaction spaces are structured, differentiated, combined, and made legible and navigable. And of course, we are confronted with a new industrial paradigm, a new science and intellectual set of paradigms. And although the engineering disciplines are also feeding into this, we need to become proto-engineers. We need to become machine builders. I mean, there's an incredible admiration to how you've been soldiering on to do all this, but in the end, it's not. We just proto-do that until we have the division of labor come through and we have machine builders on our teams. And we will be the architects on the teams, and we wouldn't have to be the machine builders, the engineers, the computer scientists. Just as a reminder, in an overall projection of your careers, to not lose sight of our specific contribution, although we have to do everybody else's work as well in a proto sense, because we don't have these set up of teams of the other disciplines at our hand, and it's very helpful to know a lot about all these other disciplines to the extent what you're learning here, to then instruct them, draw them in, orchestrate them, but the discourse of what the core competency is cannot be get lost, and that it is also performative. Aesthetic values are highly performative in society.
I would like to comment here maybe that there is one, now when I see this project in comparison to the other two of Sajay's studio, I must say that this project has me a little bit puzzled. And I think that it has to do with the other two projects that we saw, the phase-changing material and the movement of the robot. There seemed to be a real, let's say, tension between the two systems, but where every one of them was doing their best job. The robot in terms of moving to position, and the phase-changing material finding its own form with gravity and with the positioning. So there seemed to be two conflicting worlds, yet both doing their best job. Here, I am a little bit puzzled, and I don't know exactly how. Maybe, Philippe, you can help me a little bit, because the robot puts the strands in place, and there we use the phase-changing material to fix it. But really, the phase-changing material is not necessarily, or at least I don't see it, contributing per se to the formation of these strands, or to the. So I think that in a way that's what I see a little bit more linear compared to other projects, and I'm not sure what is the benefit of fixing the strands together from inside individually, so that the nylon needs to be on each one of the strands. And I wonder, for example, when you have the heater going from outside, it's a use of a robot that operates outside the bundle of strands. could you have, for example, fixed the strands together more like from a spraying perspective, for example, spraying a glue as opposed to having them individual? Or then the other question becomes, because there is this beautiful moment in the project that I thought is when you have this end effector that is actually weaving the strands together and feeding the strands, where for a moment it seems that it could be totally continuous. And it could go on and on and on and on with spools of strand. And for some reason, then in the middle of the project, you go back to this kind of modular, this is the length of the strands, we use the robots to position them, and we freeze it. But there is less this kind of idea of the continuum material that needs to be heated up and needs to be solidified because it's in a continuum. That's maybe where I am a little bit puzzled with this. Yes.
We think of the material as a continuous system, but at some point, after speculating on it and creating the technology of producing this continuous strand, we need to go one step back and validate the work we have done. The strand is not limited to 12 meters. We just test 12 meters to see how structural it is, because it's a feedback process, and we get feedback from the production and the fabrication to give it to our design process.
Actually, the behavior of the material is totally different when we have it connecting in network and we have individual strands. The active bending structures, they are behaving totally different. If we have single wires, that's totally unpredictable, and we have wires that are merged together in specific points. So this is why we want the network of the connections, so as to have the result that we expect to have.
So if you had continuous material, maybe it's a question that I don't know. If you had continuous material, how would you go about it? You would spool a portion. Let's imagine that now we scale up this to 100 times bigger. So you would begin to form this structure. You would stop. You would solidify it, and you would continue.
For them, they have to just recognize and make legible so that they can articulate that. So in your responses to Marta, I think you start to open up that the conversation is more than the assumptions that one can make from looking at it. And I think that sensitivity to that will only be something that will give even more plausibility to the things that you're doing. I think with that we should
Sorry,
let
can I
Mark
just say-
have the final comment.
I mean, I,
urgently.
I want to point out that a problem which I kind of, in a sense, sensed in the previous presentation seems to me to exist here in a slightly different way. I'll find a very brief way of putting it. There's some discussion as to almost what discipline you're in when you're doing this. I don't have a problem with that. I think you're an architect. It may be that in some sense you're currently like more towards the edge of that discourse than occupying a kind of traditional center. But actually, that's an extremely important part for the discipline as a whole, because at the edge you're presented with conceptual issues in a very stark way, which perhaps exist, you know, as more comfortable cliches if you're in the center. Now, it seems to me like any architect, you are having to live in at least two worlds at one stage when you're working. And the problem is that I think your language only attested to one dimension of the two ways. Given the extraordinary number of things that you've produced, if you track back over your language of how you described it, it was very, in a sense, low-key. We were sort of testing this and testing that, as it were, experimenting with this, experimenting with that, using, in a sense, a certain quotidian, everyday, routine language in the natural sciences. I've got nothing against the languages of the natural sciences. But that's not all that you were doing. After all, if a natural scientist was doing an experiment, he says the answer is no. You know, so you just tabulate that. We're not sitting here saying yes or no. We're sitting here trying to grasp in every way possibly, visually, etc., what you've done. It would be easier, I think, if you like, almost as a suggestion, if when you embarked on each of the stages, the tests, the whatever, you put what you were doing in the same plain, everyday natural science terms that you're putting. When you'd produced it, you should step back and write another paragraph on what you had done. Because something done is not the same as being an element in a process. It has, you know, for that moment at least, a kind of relative autonomy. My whole problem with you is that of all the people in this room, you seem to be the least to have really appreciated what you've done. Or if you haven't, then you're censoring yourself because you're thinking it wouldn't be appropriate, for example, to talk about the aesthetics of it or about the social intelligibility of it, you know, which Patrick is saying you should. Well, you know, either you're censoring or you're blind. And, you know, you need to do that second stage and not be in any sense shy to push it forward. Otherwise, you look as though you're colluding with the fiction that you don't really do architecture.
I think that's very interesting. But also slightly unfair. I would in fact expect that a jury who's been working, some of us 20, 15, 10 years in this domain and coming out of various traditions, have slightly more resources to tease out the architectural intentionality and intelligibility and how it ties on. But I want to pick up on this because I think also I'm slightly different from some of the other critics here in my emphases. And that's even doubly unfair, as these students haven't been exposed to that too much so far. But I think I want to take this opportunity because, and since to me you started to do something what I would call a kind of transcendental analytic of our conversation relative to architectural intentionality, which is not explicit, but for me it is implicit. I want to pick up on this and complete that slightly pretentious transcendental analytic, but I think it's very important. What I mean is this. Let's assume that all the machine building is done and delivered, that the engineers is handed over to the engineering is over to the engineers, and what remains as our core competency, and what this delivers, and why this is important, and why this is important. Because I think what these rigors and the harnessing of the material logic, engineering logics, performance principles, etc. First of all, of course, it does all that economic performance, technological performance, sheltering performance, environmental performance, lightness relative to the requirement of the span space. But it does that as technical functionality aspect. But what it does additionally, and that's what we love about it as well, this kind of coherency of a character, of a posture, and we have, what all this do in a sense, they deliver also, for instance, we could call it a shape grammar, a kind of unity of character recognizably across the whole range of elements and creatures at different scales. And that becomes, for me, the palette by which I now can map out and articulate and distribute the various nuanced versions of social institutional characters which need to be mapped out, painted out. That's why I've been insisting that, this is a fantastic reservoir of a new sophisticated semiology, and phenomenologically also driven semiology to create a kind of social space in the US way, because we can recognize that. We can see you can create networks of similitude, of illusion, of recognition, of difference, of contrasts, of alignment, of affiliation with these repertoires. And we need all that engineering, all that material intelligence to do that, because that's what delivers that. But I think that's the kind of, and it's implicit in some of these valuations, which which are at odds with the engineering performance criteria, which we also focus. So, and we need to recognize, that's what I call it, a kind of making explicit the implicit architectural intentionality in our intuitive choices. And I'm inviting everybody here to pick up on some of the writings where this is finally made explicit, instrumentalized, and put on par with engineering intelligences and defense and justifications on raison d'etre in terms of an instrumentality which can be put on the table explicitly. Sorry for that.
I don't know. I have to talk with Alex, with her mother and father.
Yeah, I will join you. Gonna see. But now I'm gonna meet my family.
Go, man. I am with my family. I'm going as well. I cannot stay here.
After we see him out here.
Yeah, of course.
Yes.
Συγχαρητήρια, Ζώζη.